Welcome back. In this lecture, we're going to talk about solving constraint satisfaction problems by using graph search. So here's the basic idea. We want to systematically explore the domain values of each variable by instantiating them one at a time. But unlike something like generate and test, we're going to consider a constraint predicate as soon as all its variables are bound. Because if we have a constraint that only considers, say, one variable, right away when we go and generate all those domain values, we can check if a given domain value is valid for the solution. Likewise, if there's two variables, once we have considered both of them, we could do that same type of check. So any partial assignment that doesn't satisfy a constraint, we can just get rid of. And so here's, a simple example that we had talked about earlier. We have these three variables, A, B, and C, domains 1, 2, 3, 4, A less than B, B less than C. And assignment A equals 1 and B equals 1 is inconsistent because here A equals B, it's not less. And so I don't need to worry about the assignment of C at this point because I know already just by looking at only A and B, I can eliminate anything else. And if you have a whole bunch of variables, this can save you a whole lot of searching really early on in the process. And the good news is this still guarantees a correct result because there's no way we can get a correct answer once we violated a constraint. So how do we frame this as a graph search problem? A node is an assignment of values to some of the variables. And suppose node n is an assignment for variables, let's say x1 through xk, each having values v1 through vk. So then as we move through the search, we're going to select a variable y that isn't assigned. And then for each domain value that y can have, we're going to tack that on to the end of the assignment and check for consistency. So of course, starting with the empty assignment, and the goal node is a total assignment that satisfies all constraints. So now the search space depends on which variable is selected to be assigned for each node. Now, there would be no cycles or multiple paths to a node in this way. So let's go back to our simple example of A, B, and C. Each can have value between 1 through 4 are the natural numbers, and we have the constraints A less than B, B less than C. And this is what the search tree looks like. So again, we start out with no assignments. Now, notice here, I didn't order it starting with A. The ordering, this will proceed correctly regardless of the ordering, although it may be less efficient in terms of runtime for certain orderings. So we start by checking node B. And so right away, B equals 1. We then check node A we check variable A as the next node. But notice with B equals 1, all the assignments of A cause a constraint to be violated. So we don't proceed any further, and this branch of the tree is effectively pruned. So next, going up, we to the empty set, and now with the assignment of B equals 2, we have A equals 1, which satisfies the constraints, and now we can start checking on C. 2 constraints violate C, 2 satisfy, and right away we have a satisfying assignment here. Now if we're looking for all solutions, we continue to search more, but notice with the other assignments for values of A, we don't have to proceed any further because they don't satisfy that. And we could see, looking on the other side of the tree, we encounter a similar thing for the other values of B. Also notice that here, we are just selecting a variable that's not been examined yet. You could enforce an ordering among variables, but again, you don't really have to in order to ensure correctness, although this may affect runtime. So anyway, that concludes our discussion on using graph-based search to solve a CSP. Please stay tuned for more content.